So in this unit, we'll look at the most basic equations and the most basic types of problems that you might see on the FE exam pertaining to air pollution. What I've done here is I've tried to provide you with some screenshots so that you're aware of the type of information and the location of the information that you would need for these problems. So for example, this screenshot comes from the environmental engineering section. On the other hand, this screenshot on the ideal gas law comes from the chemistry and biology section of the FE reference handbook. And this screenshot on the conversion from micrograms per cubic meter to parts per billion is from the environmental engineering section. So in this unit, we'll go through a number of sample type problems that use the information that is provided from these different sections of the FE reference handbook. So this first example, relatively straightforward. You're given a concentration of sulfur dioxide at 30 parts per billion, and it's measured at a temperature of 70 degrees Fahrenheit and 30.38 inches of mercury. And you're asked for the sulfur dioxide concentration in micrograms per cubic meter. Now, in terms of information, you'll need conversions from the units and conversion factors section. So you need conversions for both temperature and pressure. And I've just given you some information about a standard atmosphere in various different units. So let's look at this example. We're told that we have 30 parts per billion of SO2. The temperature is 70 degrees Fahrenheit, and the pressure is 30.38 inches of mercury. So, as I mentioned, we need a number of conversions, and those conversions include converting temperature to Celsius, and temperature in Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8. So that is 70 minus 32 over 1.8, or 21.1 degrees C. And the pressure is 30.38 inches of mercury, and using the conversion factor that was previously given, we'll multiply that by 0.0334, and that is 1.01 atmosphere. So the equation that we need is from the environmental engineering section, and it is micrograms in cubic meter is equal to parts per billion times the pressure times the molecular weight divided by RT, where pressure is in atmospheres, and R is equal to 0.0821 atmosphere liters moles Kelvin. Temperature is in Kelvin, so we have the concentration is 30.0 parts per billion times the pressure, and the pressure is 1.01 atmosphere, times the molecular weight. The molecular weight for SO2 is 64 grams per mole. We'll divide that by R, 0.0821 atmospheres liters moles degree Kelvin. Multiply that by degree Kelvin, and that is 21.1 plus 273.15, and that is equal to 80.7 micrograms per cubic meter. We can go back to the previous problem and choose the correct answer of 80.7. So again, I'm providing you with some additional screenshots. This screenshot is from a section referred to as PBT behavior. It's on ideal gas mixtures, and it's useful for converting to mole fractions, to mass fractions, converting mass fractions to mole fractions, so back and forth. Also for determining and calculating partial pressures or partial volumes. Now this section is from the chemistry and biology section. If you need the ideal gas constants, you'll need to look at the units and conversion factors section for those values. So let's look at this problem that involves some basic stoichiometry. So a person drives 21.7 miles to and from work each day. The vehicle that they're driving gets 30 miles per gallon, and you're asked to calculate the pounds of CO2 that are emitted during their daily commute. So I've given you some additional information. One is that gasoline is often represented as octane. That information would be likely given to you. And I've also given you a balanced equation for the oxidation of octane to CO2 in water and the density of gasoline. So let's look at this problem and we'll work through it. So as we stated, a person drives 21.7 miles to and from work each day. The vehicle gets 30 miles per gallon. So we can calculate the gallons per day that are used in commuting. So we have 21.7 miles divided by 30 miles per gallon. Miles cancel, and that is 0.723 gallons. So we're given the density. We can calculate then a mass. So we have 6.1 pounds per gallon. We'll multiply that by 0.723 gallons, and that is 4.41 pounds. And I'm going to convert everything to metric units, and then I'll convert back. So we have 4.41 pounds divided by 2.2 pounds per kilogram. You can get that conversion in the unit and conversion factors section. However, there's some information like that I would advise that you just simply know, so you don't have to look for that, and that is 2.0 kilograms. The molecular weight of octane is 12.01. I'll do this in kilograms per kilomole times 8 plus 1.008 kilograms per kilomole. First was for carbon, second is for hydrogen, and we'll multiply that by 18, and that is 114.2 kilograms per kilomole. So if we divide that 2.0 kilograms per 114.2 kilograms per kilomole, kilograms cancel, and that is 0.0176 kilomoles. So that's kilomoles of octane. If we then multiply, we have 16 moles of CO2 produced per 2 mole of octane. So we're multiplying that by the stoichiometric coefficient times 0.0176 kilomoles, and we could, let's put this both in kilomoles, and this is kilomoles of octane, and that is equal to 0.1405 kilomoles of CO2. Okay, so kilomoles of octane cancel, and we're left with kilomoles of CO2. And then we'll multiply that kilomoles by the molecular weight of CO2, which is 44 kilograms per kilomole. And since the answer was requested in pounds, we'll then multiply by 2.2 pounds per kilogram. So kilogram cancel, kilomoles cancel, and our answer is in pounds, and that is 13.2 pounds. So the answer to this is for each day that this person drives to and from work, that vehicle is emitting 13.2 pounds of CO2. And the answer is 13.6. I apologize, I said 13.2 previously. The answer is 13.6. So 13.6 pounds of CO2 were emitted each day on the daily commute. So let's look at another problem. Here, you're told that you have 30.0 liters of gas. The temperature is 293 Kelvin, and this volume of gas contains 16 grams of methane, 2.8 grams of nitrogen, and 4.4 grams of carbon dioxide. And all the compounds are in the gas phase, and you're asked for the total pressure in this container. So we have all the information presented here from the previous problem, and let's start working through this systematically, starting with methane. So we're told that we have 16.0 grams of methane. The molecular weight for methane is 16.04 grams per mole. So we can calculate the number of moles, and that is 16.000 grams, and we'll divide that by 16.04 grams per mole. Grams cancel, we have our answer in moles, and that is 0.997 moles. We can do the same for nitrogen. So we have 2.8 grams of nitrogen. The molecular weight for nitrogen is 28 grams per mole. So again, we've got 2.8 grams. We'll divide by 28 grams per mole, and that is equal to 0.1 mole. And for carbon dioxide, we have 4.4 grams. The molecular weight is 44 grams per mole. So we have 4.4 grams divided by 44 grams per mole. Again, grams cancel. We have our answer in moles, 0.1 moles. We need to use the ideal gas law. So we've got PV equals nRT, and then P is equal to nRT over V. And we'll start with methane. So we have 0.997 moles. Multiply that by the ideal gas constant, 0.0821 atmospheres, liters, mole, Kelvin. We'll multiply that by the temperature, it's 293.0 Kelvin. And then we'll divide that by the volume, 30.0 liters. So moles cancel, liters cancel, Kelvin cancels, and we have an answer in atmospheres. So we'll add that here. We'll do the same set of calculations for nitrogen, and there the pressure is 0.08, and the pressure for CO2 is also 0.08. 8. And if we add that together, the total pressure is 0.956, so the answer would be closest to 0.96 atmospheres. Let's look at this example here, which is really a modification of the ideal gas law problem that we just did. So in this case, we have a stacked gas, and it's emitted at a measured flow rate of 8 cubic meters per second. The temperature of the stacked gas is 220 degrees C, and the pressure is 120 kilopascals. The flow meter that was used to determine the flow rate was calibrated at 20 degrees C and a pressure of 101.325 kilopascals. And in this case, you're asked for the actual flow rate of the stacked gas. So let's write down the information that we have. We're told that we have a volumetric flow rate of 8 meters cubed per second. The stacked gas has a temperature of 220 degrees C and 120 kilopascals. And the flow meter was calibrated at 20 degrees C and 101.325 kilopascals, or 1 atmosphere. Now remember, the meter actually only knows how it was the conditions at which it was calibrated. So this flow rate here pertains to the calibration conditions. The other thing is to remember that Q is actually volume over time. It's a volumetric flow rate. And if we remember that V1 P1 over T1 is equal to V2 P2 over T2. So that's the equation that we need. So we'll use V1 as the calibration conditions. So we have 101.325 kilopascals as our pressure. The volume is 8 cubic meters. We're going to use the flow rate. So just remember that it's a volumetric flow rate. And we will divide that by the temperature in Kelvin. And that is equal to 120 kilopascals times our volumetric flow rate. Remember, that's volume over time. And we will divide that by the temperature in the stack. And we're converting those temperatures both to Kelvin. We need that temperature, remember, needs to be in Kelvin. And then when we solve for our volumetric flow rate, it is 11.36 meters cubed per second. So this is the actual true flow rate from the stack. The other equation that we should think about is Rayout's law. And Rayout's law says that the partial pressure of a component I is proportional to the mole fraction of that component times its vapor pressure of the pure component at the temperature of the mixture. This next problem pertains to Rayout's law. So we have a situation where we have a 55-gallon storage drum, and that contains a mixture of chemicals, all of which are liquid. So we have 400 grams of benzene, 400 grams of xylene, and 40 grams of water. The temperature of the mixture is 60 degrees Fahrenheit, and you're asked to determine the partial pressure of water in this system. Now, to do this problem here, what we need to do is we need to start thinking about the information we have. So you're told you've got a 55-gallon drum. All of our chemicals are in the liquid phase, which means that we can use Rayout's law. So we have 400 grams of benzene. We have 400 grams of xylene. And we have 40 grams of water. So that is the composition of this mixture. We need to calculate the number of moles of each. So let's just calculate the molecular weight of each. So we have molecular weight of benzene. Benzene is C6H6. And molecular weight then is 12.01 times 6 plus 1.008 times 6. And so when we calculate the number of moles, it is just simply that 400 grams divided by this molecular weight. And I haven't calculated the molecular weight. I actually did the problems in Excel, but you would need to calculate the molecular weight, and that is 5.12 moles. Okay, for xylene, xylene is C8H10, and the molecular weight then, similarly, it's 12.01 times 8 plus 1.008 times 10, and we'll do the same calculation. 400 grams divided by the molecular weight of xylene, and that is 3.77. And then the molecular weight of water, we've got 40 grams, and we'll divide that by the molecular weight, grams per mole. It's 18, and that is 2.22. So we need to sum the number of moles of three components. That is 11.11 moles. And then we need to calculate the mole fraction of water. And that is equal to 2.22 divided by 11.11. And then what we need is we'll need to multiply that by the vapor pressure of water at 60 degrees. That is 0.26 psi. Notice this is actually from the fluid mechanics section. And so then we will multiply to get the partial pressure of water. That is equal to 2.22 divided by 11.11 multiplied by 0.26, and that is equal to 0.052 psi. So that would be the answer for this problem. Now the next set of problems that we'll look at pertain to Henry's law. So again, we've got a screenshot. Note that this is actually from the thermodynamics section. So again, we've got a different section. And Henry's law can be used for relatively low concentrations. And it just simply says that the concentration in the gas is proportional to the concentration in the liquid. Now be very, very careful with when doing these Henry Law's problem. This is empirical. The units vary significantly on Henry's law constants. So check those units. So in our last example, we'll look at the application of Henry's law, or essentially this is a gas transfer between the air and water interface. So the concentration of carbon dioxide measured at Mauna Loa, Hawaii on the 18th of May, 2021 was 419.92 parts per million. The Henry's constant for the dissolution of carbon dioxide into water is given here at 20 degrees. We'll work this problem at 20 degrees. The concentration of carbon dioxide in water is what you're asked for, and we'll assume that we have equilibrium, which means that we can apply Henry's law. So we have the same information here. So we're told that the concentration is 419.92 parts per million. If you remember from class, if you've taken for ENA 489, we talked extensively about this, and parts per million is by volume. So that's an important piece of information. And you also remember this is 419.92 parts of CO2 per 10 to the 6 parts of air. Now, this then is equal to 0.00042 atmospheres. Just think about the fact that pressure is proportional to volume. We just looked at that in terms of Raoult's law, in terms of the mole fraction, which moles and volume are proportional, and therefore we can simply write this concentration. Know that this concentration in parts per million by volume can also be written as atmospheres. And you're given a Henry's constant, and that is equal to 3.4 times 10 to the minus 2 moles per liter per atmosphere. Be very, very careful with your Henry's constants. Check the units. These can be written as pressure divided by the liquid concentration. The units vary significantly from constant to constant, so make sure you know what the units are. And the aqueous concentration is equal to the Henry's constant times the pressure, and that is equal to 3.4 times 10 to the minus 2 moles per atmosphere times our pressure due to CO2, and that is equal to 1.43 times 10 to the minus 5 molar. So that is the aqueous concentration of carbon dioxide at equilibrium with a atmospheric concentration of 419.9 parts per million. So this ends this unit. Good luck on the FE exam. Hopefully this helps you to, one, get acquainted with the FE reference handbook and to review problems related to air pollution. So good luck. Have a great day, and thank you for listening.